Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through section 6.1, Discrete Random Variables. In this section, we are also going to come back to lists, so there is going to be one list that we'll be using today, or technically two. If you go to the top of page 2, or I guess in the middle of that, you'll see X, which I have in list 1, the numbers 0 through 6, and then the frequencies in list 2, which are the numbers 10 that go down to 3. So please make sure that you have those for today's or this video's lecture. Okay, so with discrete random variables, what we're going to be talking about is how to find really the probability of a specific amount of things happening. We've kind of already done a few of these, but some of them we've been doing with problematic amounts of successes because they're not as easy to exactly do. Most of the time we have to find the probability of something happening and then how many ways overall it can happen. So we're going to be addressing how to more efficiently do that in this chapter. First, we have a random variable is a numerical measure of the outcome of a probability experiment. We say that it's random because we don't necessarily know what's going to happen. Overall, a lot of these definitions may be familiar to you and is a little bit of recap because we talked about random variables before. We say that a discrete random variable has finite or countable number of values. We also have this in chapter 1, meaning that you can count on your fingers how many different possibilities there are. A continuous random variable has an infinite amount of outcomes, means there's an infinite amount of possibilities between any given range. In this chapter, we'll talk about how to deal with discrete random variables. In chapter 7, we'll deal with how to deal with continuous random variables. A probability distribution, also something we talked about at the beginning of chapter 5, is it provides the possible probabilities for a random variable corresponding to however many ways it can happen. So just what is the probability for any given outcome in a probability experiment? Typically given as a table, but could also be given as a graph, which we are going to show later on. Some rules for probability distributions. The sum of all probabilities should equal to 1. Which you should be familiar with, and all probabilities need to be between 0 and 1. No probabilities that are negative, no probabilities over 100%. One of the new things is how to find the mean of a probability distribution, and I say new with quotes, so quote-unquote new. If you are trying to find the mean of a probability distribution, what we're going to do is take the sum of each value, which is x, times the probability of that value, or p parentheses x. The reason I don't necessarily say this is new is because this is more or less the formula for frequency mean. We had the formula for a frequency mean a while ago as the sum of x sub I times f sub I over the sum of f sub I. Well, if you take each frequency and divide by its total, what you get is a probability. So this is really the exact same thing as taking each value and multiplying by its probability. However, this is a more compact way of doing this. We're going to be using this pretty often because the mean is going to be basically the most important part of section 6.1, and that mean is also going to be known as an expected value. An expected value is another way to say the mean of a probability distribution, which is what we expect to happen in the long run. Overall, what do we expect to happen from each trial of this experiment in the long run? That's what the expected value is. However, since the expected value is basically the same thing as a mean, this section of 6.1 should be a nice recap over some things since really chapter 2 for you, before we move into 6.2, which is where we introduce some real new stuff. Lastly, there's this note, just remember that the law of large numbers exists. As the number of repetitions of an experiment increases, the mean value of n trials approaches the population mean. That's what mu sub x means. Therefore, if we find the expected value, which is what we expect to happen in the short term, we can then extrapolate that to what's going to happen in the long term. Overall, if we do an experiment more and more and more, how much do we expect to actually gain or lose? We'll be doing a lot of expected value with gambling kind of context in terms of how much monetary gain there is, and you'll see some examples of this later on in this video. Overall, in order to do a mean, we're still going to do our old friend back from chapter 2 and 3. We're going to be doing one-var stats yet again. If you forget how to do that, that is in the stats section. So hit stat, and it'll be over in calculate, and it's the first option there. We're going to be doing one-var stats with both values and probability lists. So we are going to be doing with both the list and whatever we have for the probabilities. But let's do an example of that here. First, we have this situation that says, what is the ideal number of children to have in a family? The following data represents the ideal number of children for a random number of 900 adult Americans, a random sample of 900 adult Americans. So these 900 adult Americans were surveyed, and they asked, how many children would you like to have in a family? And we have responses from between 0 and 6 children. The first question asks us to construct a discrete probability distribution for the variable x. What that means is that we're going to take all my values here, and instead of pairing that with a frequency, what I want to do is instead pair that with a list that has probabilities. So I want to find probabilities for each of my values here. So I'm going to extend this out a bit. Now, I asked that you had these lists in your calculator here, and that's because we can find the probabilities a lot faster than doing one at a time. I have all the frequencies in list 2, and I can easily make those into probabilities by adjusting list 3. So I'm going to go over to list 3, highlight the top of it, and what I'm going to do is say for list 3, take all the values from list 2, the frequencies, and I want to divide those frequencies by the total frequency, which is 900 adult Americans, as given in the description. So L2 divided by 900. If I do that and hit enter, I should get all the probabilities I'm looking for. So I'll round to 2 decimal places. I'll do 0.101, 0.03, 0.58, 0.28, 0.08, 0.02, and I guess 0.003. So I'll round that last one because it didn't have 2 decimal places. Okay, so that would be the probability distribution given right here. Now we want to compute and interpret the mean of the random variable x. Now to compute the mean, what we want to do is take the values and the probabilities and set those into lists and run one-var stats. So what I'm going to do one-var stats. Remember, in order to show your work, always write down your program and your inputs. In this case, I'm going to type in L1, which is my first list, the x values, and then my frequency list, or in this case, my probability list, which I have in list 3 now. So I'm going to do stat, over to calculate, one-var stats, do L1, and then for my frequency list, I'm going to do L3. Now, when you're showing your work and writing down your program, I've said this before, but do not write down inputs here. The instructor that you have should know where one-var stats is, and I highly bet that they do know. So you do not need to say stuff like stat, go to calculate, go to number 1. We don't need to know that stuff. We know where it is. Just say one-var stats and the functions you put in. Overall, we have our mean here, x bar, because this is a sample, so we'll say it's x bar, not mu. X bar is 2.45 children. So that would be the mean. In order to interpret this, we look at 2.45 and note that that's not a realistic number of actual children. You can't have 2.45 children in a household. What we would instead say is that on average, we expect that an individual to like somewhere between 2 and 3 children. That would be a nice interpretation of this. So on average, we expect a person to want somewhere between 2 and 3 children. That's where 2.45 is. Now C asks us to compute the standard deviation, and if you notice on my screen I still have 1var stats and I can find my standard deviation, but if you notice I don't have Sx. The reason why I don't have Sx is because I found the standard deviation using probabilities. And if you remember, the old formula for the standard deviation for a sample, I'll write it up here, the standard deviation of a sample looked like this. Sum of each value minus the mean squared, the square deviations, and then for a sample standard deviation, we divide by n minus 1. Well, in this case, when you sum all your probabilities, as you can even see on the calculator here, the sum of all probabilities is 1. So this would end up being 1 minus 1, which is 0. And you cannot divide by 0. Therefore, you will not get a sample standard deviation from this. You will only get a population standard deviation, which is what we're looking for. So we have the population of this random variable to be 0.83, or population standard deviation. That's how much it spreads. Okay. And technically, you would actually say that 2.45 is mu sub x bar, but either way. Now, D asks us to graph the discrete probability distribution, and I already have this graphed for you, although there should be a label here, and there should be a title. I already have this graphed for you so you can see how a discrete probability distribution is graphed. It's graphed kind of like a mix between a histogram and a bar graph. In this case, we're not drawing it like a histogram because we're not going to have this bar continue on this way and this bar continue on this way and on like this. We could theoretically do that if we wanted to, because this is a quantitative measure. However, it doesn't really make a lot of sense to do that because we're not going to get any values between 2 and 3 or between 3 and 4 because these are discrete variables. So when you draw a discrete probability distribution, you do it very, very simply. You simply find the discrete values 0 through 6, and then you draw a bar vertically that goes up to where the probability is that we have labeled on the y-axis. And that's all you need to do. Last question, what is the probability that randomly selected adult family thinks the ideal number of children is 2? Well, based on my probability distribution, we got 0.58 from that. So I'd say the probability of 2 is 0.58. Okay, now most of this really should be recap in terms of how to find a mean, standard deviation, how to do divisions with lists. Even this graph, which looks a little bit different, is more or less the same thing as a histogram. Page 3, however, is going to introduce and work with expected value. So this is really where we do a lot of expected value problems. And expected value is the main point or the main topic in section 6.1. We have here, in the game of roulette, a player can place a $5 bet to bet on the number 17 and have a 1 out of 38 chance of winning. If the metal ball lands on 17, the player will win $180. Otherwise, the casino will take the player's $5. Now, in order to do these expected value problems, it may ask you to make a probability distribution, it may not. However, we're going to do this in either case. This setup is what we want in order to solve expected values. This is a nice way to organize all your data. You're going to have first your events, followed by your value, followed by the probability. Now, in these ones, thankfully, expected values, the table should not be too long because there's not many events that can happen here. In this situation, when you're playing roulette, you can either win or you could lose. Technically, you don't even need to have this part of the table made, but I always recommend it. That way you can easily label and identify what each of your rows are supposed to be doing. Very good for organization. Now, I'll deal with the value in just a second. First, I want to deal with the probability for now. The probability of winning, as it says, there's one number out on the board, and it says that there's a 1 out of 38 chance of winning. So the probability of winning is 1 out of 38. Alternatively, losing should be the complement of that. There's 37 out of 38 chance of winning. Because this is a probability distribution, that means that these probabilities should sum to a total of 1. So So we do need to make sure of that. If you don't know how to find a given probability like this, you could always find this by doing 1 minus 1 out of 38, because you know the total should be 1. So that's how you would find the probabilities, which isn't too bad. The next point, though, is to find the values. We need to be careful here. This is where most mistakes end up with expected value. With win, if you win, it says that you win $180. However, what we need to keep in mind is that the player placed a bet of $5 initially. What that means is that they're not necessarily going to gain $180. That's how much money they won from the game. What they're going to gain is $175 because they already put $5 down. So they had a net gain of 180 minus 5. They have a net gain of $175 if they win. So that is going to be my value here, $175. If they lose, they will lose $5 because the casino will take that. However, to represent a $5 loss, what we will do is put a negative there. Say negative $5. That is the value of losing a game to you. Now, to find our expected value, you recall the expected value is the same as the mean for a probability distribution. In order to find the mean of a probability distribution, all we need to do is take x and multiply by the probability of x. So we're going to take each probability and multiply by, or each value multiply by its probability, and add the results together. So we're going to do 175 times the probability of 1 out of 38. And then we're going to add negative 5 times 37 out of 38, which is really subtracting 5 times 37 out of 38. We put all that together in our calculator here. We have 175 times 1 out of 38 minus 5 times 37 out of 38. Notice the way that I type it in is exactly how I have it written there. I want to be careful to make sure I don't mess around with any operations. And what we get is an answer of negative 0.26. Now, questions have been in the past of how do I know when to round, and generally you just want to keep as many decimals as you can. I always like 3 or 4, but this case I rounded 2 decimal places. Why? Well, because we're dealing with expected value. And in this case, the value that I'm dealing with is in dollars. Therefore, this is negative 26 cents. That's why I rounded 2 decimal places, because money always goes down to 2 decimal places. Now, if I just step back and look at that, and I see that the expected value of playing the game is negative 26 cents, that doesn't make a lot of sense, because that doesn't mean that if I play this game, I'm going to lose 26 cents every time, or on average. It doesn't mean that that's actually going to happen when I play a game or two of this, that I'm going to lose that much money. This is what's going to happen in the long run. So if I were to play this multiple times, for example, if I were to play this 1,000 times, I can use that expected value to determine how much I expect to lose or gain. That calculation is nothing complicated. I simply need to take my expected value, and if I want to see what would happen if I played 1,000 times, I simply times that by 1,000. Negative 26 cents times 1,000 will give you negative $260. You can see that here. I'll do negative, make sure you use the negative next to the decimal, 0.26 times 1,000 to get negative 260. Now that makes a lot more logical sense. That's more possible to do when gaining 175 or losing 5 in every instance. It's possible to get down to that kind of a number. So this makes a lot more sense, and that's also how we'll typically interpret expected value, by trying to put it in terms of doing it many, many times. That should also make you think of how we interpreted probabilities back in Chapter 5. All right, one more example of this. A life insurance company sells $250,000 one-year life-term insurance policy to a 20-year-old female for $200. According to the National Vital Statistics report, the probability that a female survives the year is 0.999544. Compute and interpret the expected value of this policy to the insurance company. Notice that there's a big blank here. This is how I personally like questions too, because this is how people would theoretically do things. They just have an open canvas and they have to solve things. Well, the way we're going to do this is how we did the last one. We're first going to set up a table and have events. We're going to have the value of those events, and we're going to have the probability of those events. Now, in this case, what could happen to this individual, this female, is that they either live or they die. It's a little bit morbid, but that's what we're considering here when we're looking at life insurance. What we also need to keep in mind is the last sentence here that says, compute and interpret the expected value of the policy to the insurance company. So we're going to determine value based on the insurance company. If that individual were to live the year, then that means what happened overall was that female paid for the insurance and the insurance company did not need to pay anything in return. So that means for the insurance company, that individual living is a net gain of $200 to them. If that individual were instead to pass away, then that means that the individual paid $200, but then the insurance company paid out $250,000. So overall, $250,000 minus 200 gives us 249,800. That's how much the insurance company would have to pay out. Therefore, that's a negative 249,800. So those would be the values to the insurance company. That last sentence is important because that'll dictate where that positive and negative go. Now we are given that the probability of the person living is 0.99 or 999,544. And if we need to find the probability of somebody passing away, that's going to be 1 minus that. 1 minus 0.999544. We do that, we get 1 minus 0.999544 will give us a small number that is in scientific notation, 4.56 e negative 4. Now you can use that as it is in your calculator, however it's kind of complicated to do so. What we can instead do is transfer it into a decimal by taking 4.56 and moving the decimal place back 4 times. So 1, 2, 3, 4, and we fill in the blanks with zeros. So that gives us 0.000456. So that's our full table that has all the data that we need, and we can find our expected value now by doing 200 times the probability minus the 249,800 times its probability, 0.000456. With this one, we should get a nice whole number for this. 0.999544 minus 249,800 times 0.000456. Whoop. That last one was I put in a negative instead of a parentheses. There we go. We get a value of 86. Note that the value before was in dollars, so that means this is $86. Now again, this does not mean that if the company were to sell life insurance that they are going to make exactly $86. This means that in the long run, if they sell many of these, they would gain $86 per policy that they sell. This does not mean that just selling one insurance policy will get them $86 guaranteed. That's not how that works. This is a long-term thing. So, for example, if they were to sell 500 of these, I would have 500 times 86, and they would expect to gain $43,000. Okay, so with that said, that's everything for 6.1, going through expected value and how to apply those situations. You should be able to go through and complete the homework for section 6.1 at this point. If you have any questions, feel free to put those into the comments below or ask your instructor directly. I hope you have a nice day.